Okay, we're going to kind of wrap up the last couple of chapters and tie a nice neat little bow around it in chapter 41, and we're going to talk a little bit more about atomic structure. So now we're going to write the Schrodinger equation that we played with in the last chapter in 3 dimensions and apply that to a 3-dimensional box. And then really a hydrogen atom is kind of like a 3-dimensional box, so it's going to extend to talking about the hydrogen atom. We'll talk about how electrons are kind of spinning as they go around a nucleus, and if we apply an external magnetic field to it, it's going to affect their motion. So we'll talk about spin, and we'll talk about the Pauli exclusion principle, which is kind of like a zoning ordinance for electrons in multi-electron atoms, and we'll finish off by talking about X-ray spectra. So up until this point, we have talked about the Bohr model, which will describe an atom kind of like nucleus with an electron revolving around it, and I still will refer to that because I think it's conceptually easy for your mind to swallow. But we do know that electrons are behaving like waves as they exist inside of their orbits. So we need to use quantum mechanics to describe this. And it also turns out that if we have more than one electron, that we are going to have electrons that live inside of these shells. And why can't so many of them live inside of, say, the innermost shell? Well, it has to do with electron spin and something called the exclusion principle. And this chapter is really going to start to look a whole lot like chemistry, because physics really is the basis of chemistry. And what we want to think about with these nice little pictures here is take a look at lithium versus helium. Really, there's just one extra proton and one extra electron, and these two creatures are very different. Lithium will spontaneously catch fire if you drop it into water, whereas helium is really, really, really light. So we actually live in a 3-dimensional world, and in chapter 40 we dealt with wave functions that were just kind of a function of x and maybe time. However, in reality, we actually need to write our wave functions as a function of x, y, z, and time. And we can pretty much directly extend the one-dimensional Schrodinger equation that we played around with in chapter 40, kind of as such, where this is actually a h bar. Now, solving this beast is actually quite complex, and we're not going to be solving it. I do want you to know that it exists, but more importantly, I want you to understand some of the realizations that come from this equation. Now, if a particle has a mass m and an energy E, then we can say that it's going to have some stationary states which are not going to depend on time, just like we did for the one-dimensional Schrodinger equation. So we can kind of take this guy and break out the time variable as such and call that a stationary state. And this is going to lead us to the Schrodinger equation in 3 dimensions, which looks and tastes and feels and smells just like it did for 1 dimension. Now what we can do is we can take our Schrodinger equation in 3 dimensions and apply it to a 3-dimensional box and say that this box is going to extend from 0 to L on the x, y, and z axis. And you can kind of see the box drawn right down here. Now, it's essentially going to look, the solutions are going to look just like they did for a one-dimensional box, where in the x direction it's going to kind of go like a sine of, now we're going to say nx pi times x over L. And the same thing for the y and the z. And only certain energy levels are going to give us stationary states. So there's only going to be certain allowable energies. Now, we have 3 quantum numbers now. Now we're going to have nx, ny, and nz, just kind of extending what we learned from chapter 40. Now, something that's kind of interesting in a 3-dimensional box is states can be degenerate. And what I mean by that is that they can have different values of nx, ny, and nz, but they will have the same energy. Now, kind of an example of that is if we were to look at, say, nx being equal to 2, ny being equal to 1, and nz being equal to 1, then we're going to get some wave function, and it's going to kind of look like this. And actually what we're looking at here is we're looking at kind of a probability distribution here. Where are we most likely to find an electron that we threw in this box? This one right over here has the most probability of being there or there, with very little probability of being at the ends. Now this has some certain amount of energy. I'll talk about what that is in a little bit. But if we were to look at nx being equal to 1 and y equal to 1, but now nz is equal to 2, the wave function is going to look very similar. We're going to have the most probability now here and here, but really this looks a whole lot like it did right here and right here. These two states will have the same energy, and you can convince yourself that nx equal to 1 and y equal to 2 and nz is equal to 1 will also have the same energy, only this guy, it's going to, the probability is going to be sideways if you were to look at this kind of from above. One important thing to keep in mind about degenerate states is that the electrons cannot have the same quantum numbers. So we can't have an x equal 1 and y equal 1 and z is equal to 1 for more than one electron. So electrons can't share the same quantum numbers. So what do the allowable energy levels look like for this three-dimensional box? Well, it looks a lot like it did for a one-dimensional box, only now we have 3 dimensions to kind of worry about, and 3 quantum levels. Now, the total energy is just going to be the sum of all those guys, and we can go ahead and write that guy like this, right down here, where this is just nx and y and nz all added up together. Now, what do these energy levels kind of look like? Well, having nx equal to 1 and y equal to 1 and nz equal to 1 is going to give us some ground level energy. And keep in mind that if we add electrons in a box, this is the level that they want to be in. And if they can shed some energy and drop down to this level, then they will. Having the quantum levels right here, you can see this state right here, the second one, is going to be degenerate, meaning that there's 3 possible combinations that will give us this energy. And actually, you can convince yourself that this energy is going to be 2 times E1. We can move up to the next energy level, and that's going to be degenerate as well, with 3 degeneracies. And then up here, you can kind of see this one's going to have 3. There's only one way to get to the 4th energy level, 222, and there's actually 6 ways to get to this one right over here, 1, 2, 3, 4, 5, 6. And you can, as you can imagine, it gets more and more complicated as we get to higher values of n. One thing to kind of keep in mind is we could get rid of this degeneracy by setting Lx not being equal to Ly not being equal to Lz. This will get rid of this degeneracy. But that's an even more complicated problem, so let's not go there. So what I want to do from here is kind of take a look at how the Schrodinger equation can apply to an atom, and just want to take a quick look at the progression of our model for the atom. We started with just a positively charged nucleus with an electron just kind of whizzing around it. This led us to treating it like waves, to these de Broglie waves that had to have certain energy levels, certain circumferences that were allowed. And now we're going to kind of progress to this right here, which is kind of the Schrodinger model, which says that we can treat these electrons like waves, and where are we most likely to find them? Well, that's going to be where the dots tend to have the largest concentration. There's going to be places where we're far more likely to find an electron than other ones. So let's go ahead and talk about how the Schrodinger equation can apply to the hydrogen atom. Now, it does turn out that it's a lot more convenient to write the Schrodinger equation in terms of r, theta, and phi rather than x, y, and z, because if you think about it, if we treated this like a positively charged nucleus with some electron that's kind of whizzing around it, it makes a lot more sense to move to spherical coordinates rather than Cartesian. And I can assure you that that transformation is a whole lot of fun, and if you take a higher level physics class, you'll definitely see that. We're not going to talk about it too awful much. What I care about a lot more is going to be some of the implications of this. And the implications is that we're going to have some stationary states with some quantum numbers, just like we had nx, ny, and nz for a particle in a box. And these quantum numbers are discrete, and we're going to have n, which is going to describe the energy, L, which is going to describe the orbital angular momentum, and then m sub L, which is going to describe the z component of the orbital angular momentum. And just to kind of scare you, what we do is we're writing our wave function, again, as a function of r, theta, and phi, and the Schrodinger equation is going to break down as such. Again, it's been solved before. You'll solve it in a higher level physics class. What I care about a lot more about this equation is that we have these quantum numbers, ml, l, as well as n. Now, what falls out of the Schrodinger equation when you go ahead and solve it is it turns out that the energy levels have got to be discrete, and it's the same exact energies that we found with the Bohr model, so we get a warm fuzzy feeling about that. And how much energy? Well, that's going to be equal to this nasty creature right over here, which is going to work itself out to be negative 13.6 electron volts divided by n squared, where keep in mind that that n is the principal quantum number, and I would argue the most important, and the energy, or n is equal to 1, is going to be the lowest acceptable value for that. Now, some other things that kind of fall out of the Schrodinger equation is that it turns out that the orbital angular momentum, this guy right over here, L, has also got to be a quantized value, and it's related to the quantum number L as well as h bar. And right over here you can kind of see how n dictates the orbital angular momentum values. What we also find is that the z component of the orbital angular momentum has also got to be quantized, where it's related to this quantum number m sub L multiplied by h bar, and L is what dictates these quantum numbers. One thing to kind of keep in the back of your head is that these guys can be plus or minus, where these guys cannot, and what that is kind of related to is that's related to whether the electron is going clockwise versus counterclockwise, kind of. Much like a three-dimensional box, we do have degeneracy, which is having different quantum numbers but the same energy. And if we were to look at the simplest possible case and realize that we're talking about wave functions, we can talk about the probability now of finding an electron between, say, r and dr. And what we can do is, let's just take a look at the simplest possible case and say that there's no orbital angular momentum. Then the probability is going to peak right here, which is going to be what we would call the 1s state, and that's going to occur exactly where we would expect it to be, 5.29 times 10 to the negative 11th meters, which is the Bohr radius. Now, if it had more energy, then we would say n is equal to 2. It's going to peak right over there. We would call that the 2s. And then right over here, we're going to have n is equal to 3 and n is equal to 4. One thing to kind of keep in mind is when we're looking at the 2s and 3s and 4s, that the radii are going to occur just where we would expect them to based on the Bohr radius, which is that value for a that I gave you right up there. Once we start to give this atom some orbital angular momentum, we still will have degeneracy, and L is equal to 1 in a spectroscopic notation is actually going to give us the p states, and then we could have the 2p, 3p, and 4p, and these guys right here are not going to be spherically symmetrical like it will right up here. One thing to kind of keep in mind is that as we start increasing values for L, then we are also increasing our range of m sub L's, and we're going to have more degeneracy. Now this is starting to look a whole lot like some chemistry right over here, and you can kind of see that chemists like to write things with spectroscopic notation. And what's going on right here is the value for n is going to determine the electron shell, and the chemist would say that n is equal to 1 is the k shell, n is equal to 2 is the L shell, the m shell, n equal to 3, n, and n would be the fourth shell. And then L is going to determine the state, where L is equal to 0 is going to be what we call the S state. L is equal to 1, we're going to call that the P state. L is equal to 2, we're going to call that the D state. L is equal to 3, we're going to call that the F state. L is equal to 4, we're going to call that the G state, and so on and so forth. Something to kind of keep in mind as we're increasing our value for n, we're increasing our value for L, and more importantly, when we increase our value for L, then we increase our values for m sub L, and we get more degeneracy. One thing to kind of keep in mind about these probability distributions is that they are, three-dimensional. And what I mean by that, if we were to look at the zero angular momentum case, L is equal to 0, that we kind of have this shell that's going to be the n is equal to 1, and then we're going to have this guy right over here, which is going to look kind of more like a fuzzy donut, and that would be n is equal to 2, then n is equal to 3, and so on and so forth. And we're having these shells that are larger and larger and larger and larger as we get more and more and more energy. We do have regions where it's very, very, very unlikely that we will find an electron, and we have regions where it's fairly likely that we'll find an electron. Note that this does not mean that we know exactly where the electron is, and we still have the Heisenberg uncertainty principle that says, hey, if we know where the electron is, then we can't know how fast it must be going. So if we knew exactly where it was, we wouldn't know how fast it was going. So the Heisenberg uncertainty principle does still apply. Once we start talking about L is equal to 1, the p states, or L is equal to 2, the d states, then we go from having nice pretty shells like we had right over here to kind of some more funky looking patterns. They tend to usually be symmetrical, and that would be the 2p state with plus and minus 1. You can just kind of see the plus and the minus. And then we have these guys right over here.